Hi everyone, we are getting to the end of the theory, I promise. Today is a really important lesson. It's all about how we can actually learn to improve our AI algorithms, because when it comes to most people who work on AI, they're not just working on a 2-hour tutorial and coding something. They are working on these projects for weeks and months trying to figure out what to do. So today I'm going to tell you about a few tools that you can use to figure out how do I improve my AI algorithm over time. However, here is the big caveat that I'm going to say right at the beginning. All of this happens after you've coded your first implementation. Your first priority should always be, let me quickly test out, let me make a rough and dirty implementation. Doesn't matter which cost function I use, doesn't matter which activation function. Just let me see how I can get from input data to output data as quickly as possible. Afterwards, you can go and mess around with changes and try and make your, we call it model, AI model, better. However, first thing, make it quick, dirty, just get it done. So with that being said, let's dive into how, after that, do we actually make our models better. Now, there are a few key concepts that we need to understand before we get to the analysis. What data do we look at to figure out whether our AI model could use some of, this magical ingredient or that magical ingredient to improve. And the first, building block towards getting there, towards getting to how we interpret that data, is we need to understand the difference between train, test, and validation data. So when it comes to this, remember that earlier, whenever we were coding AI algorithms, we were always going from some input X and then trying to create a function that could get that X to turn into Y. So that could map from X to Y, that could generate predictions that corresponded to Y. Now, X was a matrix that had dimensions m by n, so m examples by n features, and then Y was just, m by 1, m examples. So when it comes to train, test, and validation data, the idea is, can we split that m dimension? Can we split the number of examples? So let's say let's use an example of housing price prediction. So the first 10,000 houses that I have data for, that will be, split into one data set, and the next 2,000 might be split into another, and the last 1,000 might be split into a third one. Now, specifically, we call these data sets training data, test data, and validation data. Let me explain each one. So training data has been, what we're using so far. So whenever we run gradient descents, when we're adjusting the parameters of the algorithm, then we are using what is technically called training data. This is different from test data. Test data is when we've gone through gradient descents, we've adjusted the parameters of our model, and we might have saved them somewhere. I showed a few tutorials ago how you can save NumPy arrays, how you can save values with libraries like joblib or pickle. And this test data comes into play after we've already adjusted the right parameters, we've tuned the dials and knobs of the algorithm, and now we want to check, is it actually making predictions well, given the settings that we currently have. And finally, we have validation data. Validation data is what we will use to adjust the hyperparameters of the algorithm. Remember, the difference between parameters and hyperparameters is that with parameters, the model, the AI algorithm will adjust them during gradient descent. But with hyperparameters, it's up to us to figure out, what are the values we want to set it to. So for example, the learning rate alpha, that might be one hyperparameter. Now, that's just, a dictionary definition of the purpose. Don't worry about the understanding component yet, but we'll come back to each of these so that you can get a sense of, why do we actually do this? So dictionary definition is just, train data is for the gradient descent part, test data is for checking your accuracy afterwards, and validation data is to mess about with hyperparameters. Now, with that being said, let's move on into trying to understand, well, why are we doing this? Why are we splitting up these M examples? So let's say I am training a cat classifier. So I get an image, like this lovely cat, and I'm trying to predict, in this image is a cat or not. So I might actually go and get these images from, say, Unsplash, and then use that as my training data. So, I'd run gradient descent on some kind of algorithm that would be able to go from an image like this to, predicting, yeah, there is a cat or no, there isn't. Now, I can do that with these nice HD stock photos of cats. But let's say then when I go, to actually use this algorithm, let's say I'm using the Google Lens app, that app, you just point your phone at anything, it tells you what it's seeing. Well, let's say, I actually deploy my algorithm to be used in an app like that. And then the user, they send me pictures of their cats and their cats look like this. Wow, that's a little bit different. That's a little bit different than our stock photos. And in the real world, well, of course, you're gonna have this. You might have, grainy cat photos. You might have other odd ones that our algorithm maybe hasn't seen during its training. So that is basically the idea of why train and test data exist. It's because when our algorithm is training with the data, when it's adjusting the parameters so that it can make the best predictions for these types of images, well, it might have, some cost, C underscore train, that's equal to some value. But then when it gets, to the real world where users are messing with it and, they're dressing up their cats in weird ways, then the cost is going to increase because it's now harder for the algorithm to make its predictions. It's going to be more wrong more often. That's the idea of the test data. It is kind of saying, well, if the algorithm's already seen these images, then it's going to have an easier time, when we're checking the accuracy, it's going to have an easier time getting pretty good results. However, the real test is, how does it do with unseen images? How does it do with data that it hasn't seen before during training? Because, in the real world, when we use a image detection algorithm, we're going to want to use real user data. So that's why we have the train data versus the test data, because the unseen data is like more of a challenge. It makes sure that the algorithm, it's not just, remembering, hey, during training, I did this. So, when it comes to the test, maybe I'll just, memorize that. I hope that analogy is making a bit of sense. Just to note, this is just an analogy. If you were actually training a cat classifier algorithm, it would be irresponsible to just get, high quality stock photos of cats while training and not include, maybe more realistic user photos. You want a mix of both. So that is train and test data. Hopefully that gives you an intuition. Validation data, we're going to come back to, okay? So just keep that in the back of your mind. We're going to come back to this. We're going to come back to this at the end of the lesson. For now, let's focus a little bit more on the train and test data. So what does that actually mean when, our train data is something and then our test data is a little bit bigger? What does that actually mean? The way that we interpret that and the way that we figure out, given a certain combination of train and test data, what do I want to change about my algorithm? How can I improve? Is with this concept called bias versus variance. This is really enormously important. So really, pay attention to this section. Bias versus variance, you can also think of it as underfitting versus overfitting. And hopefully when you see these visuals down below, it makes a little bit of sense. So you can see we have a regression algorithm here where we have, these dots, these white dots. They're scatter points that represents data. And we want to draw a line of best fit through this data so that we can predict, given a certain x0, what is the output that I get? So given x0 is here, then, the output at this point would be this. So this is a standard regression problem, and we have two proposed solutions. One solution, you can see it doesn't do a great job. It just goes through 1, 2 of the points, and the other ones, it's kind of not going through. And even visually, you can see the line of best fit, it should probably be like a curve like this. It shouldn't be like a straight linear line. And this kind of curve might be a square root function, if you know what that is. So this one, it doesn't seem too accurate. Now over here, well, this line is going through all of the points. Yeah, so that's good, but it seems like it's, over complicating things a little bit. You could just draw a simple line like that, and you do pretty well. I don't know if you need all of these curves here. It seems like a little bit too complicated. Now, you can imagine this is underfitting over here because it's, not fitting too well to the data. And over here, this is overfitting because it's created a more complex function than we actually need. This is called high bias versus high variance. Now, why do we have these fancy words? If you don't like the fancy words, feel free to just say underfitting versus overfitting. But if a intuition of the bias and variance, bias might be the algorithm here is pretty biased to, a certain set of data that it's getting right, and all the other data is just ignoring. Yeah, I don't care. You can just, go be somewhere else. It doesn't matter to me. And with variance, you can see that I'll get a little bit into, the exact reason why we called it variance in a second. It has to do with the cost of different things. By the way, there are equations, so this line, it could be plotted with this kind of regression equation, whereas this line, it has one of those fancy ones, the ones that I said how to avoid. So just a side note, someone asked me during the regression lesson, when do you plot a line like this versus when do you go, crazy with your parameters and features and feature engineering? Well, it has to do with underfitting versus overfitting. When you have a function that's too complicated, when it's overfitting, then you've gone too far. And here you can see when you have a function that is underfitting, when a function has high bias, then you maybe want to select a more complicated relationship. Anyway, let's now explain, why do we actually call it variance? So it actually has to do with the cost, specifically the train and the test cost. Just like you saw up above, the algorithm has different train and test costs because this data it's never seen before. When it comes to bias and variance, a key clue into identifying which is which when you don't have such a simple image to graph, because you won't always, let's say you're doing natural language processing where you have just audio It's how to visualize, oh, here's my line of best fit. So the key distinction that we should look out for when it comes for high bias is that the train and the test costs are really high. Think about why that is. So let's say, this is the training data in white. You can see the line of best fit doesn't do a great job at predicting things. Now let's say, we give the algorithm some new data. It's going to be slightly different, but not too different. So we give it some test data. So maybe, you have a data point there, and maybe there, and there. You can still see, the algorithm doesn't do a great job at fitting to that because it's underfitting. It has too much bias. Regardless of whether you're looking at the train data or the test data, they're slightly different, but overall their shape is pretty similar, and this is just not going to cut it. So it is underfitting. That's why we have both high train and test costs. For variance though, the train cost, it is much less than the test cost. This is what that symbol means. Less than, that means much less than. So why is that? Well, you can see here, so we said the white, dots are the training data. You can see that this example, this equation, it fits to all of the points. The line goes through all of the points. So the train cost is basically 0. However, again, let's say, you slightly modify the points for the testing data and, they're pretty similar, though not entirely similar. Now you can see, the line doesn't go through any of those points because it has, optimized way too much. It has overfitted too much to just this, training data, just these white points. Whereas, if you had a reasonable algorithm that was a little bit like this, then, whether you have train or test data, you'd get pretty similar costs. So that's why we call it variance, because the cost varies a lot. When you have the train data, the cost is basically 0 because the algorithm overfitted to it. But as soon as you get the test data, now it's like, wow, the cost changed so much. That's why we get this word variance, because the cost varied so much. Hopefully that's making a little bit of sense. I hope that this concept is, it makes a little bit of sense in this simplified application, because afterwards we're going to talk about how do we fix this. And we have to fix this in every single AI algorithm you will ever work on. Doesn't matter if it's regression, doesn't matter if it's binary prediction, doesn't matter if it's, neural networks, no matter what you're working on, you will have to deal with bias versus variance problems. So really, if you don't understand, please go back and rewatch. It's really important that you maybe search up the articles you need to understand these two concepts, because we're going to talk about how do we fix them. And these are practical tips that, people in the industry are using. So really, really important part right now. The reason why we need to study, how do we fix these things? It's because we have different approaches to dealing with a high bias and different approaches to dealing with high variance. And usually when we're working with AI algorithms, either we have high bias or high variance. You don't want to be in a situation where you have both. That's when you've done something really wrong. But usually we're lucky. We only have to deal with either high bias or high variance. So when it comes to dealing with each approach, we have different tools. Again, this is industry knowledge right here. So let me talk about a few tools. First of all, how do we fix a high bias? That's when the training and the test costs are both high. I'm going to explain these fancy words, don't worry. So how do we fix a high bias? One approach is that we can change, the features. We can change the parameters that we're using. So if you look at this example here, we only have one feature that we're considering and two parameters. we're graphing a linear regression line. However, if that's not working, well, maybe we could try and say, yeah, we need a little bit of a more complicated line. So maybe we could have like more features. So, not just theta 0 and x 0, but maybe we have, theta 0, x 0 plus theta 1, x1 plus theta 2, x2. And, maybe we can also modify not just these theta parameters, but also the features. So maybe not like, sine of x0 raised to the fifth power, but maybe, okay, we can do like x0 raised to the 3 plus, x1 later on, that might be squared. So we can use like more complicated features and parameters. And I hope you can see why, let's say we have a curve like this, or even a curve, a little bit, closer like this, then that might fit the data better. So that's why we can, change not just change, but specifically increase the number of features and parameters. When it comes to neural networks, we'll talk about that soon. We can also add more layers. Don't worry if you don't understand what that means right now, you will soon. Another thing that we can change in our model is the hyperparameters. So, maybe the reason why our line of best fit is not fitting. So let's say you even, got a curve, but you were getting out this. Maybe it's because, you only did 50 iterations of gradient descent. Maybe you want to do 500 instead. And that might get, a line of best fit that's closer towards what we actually want. So, the number of iterations, that's one example of a hyperparameter that you could change. Another thing is regularization. This is really important, but you don't know what it means yet. Don't worry, you will in just, a few seconds. So just hold on. Another thing that we can try and change is the optimization algorithm. So I talked a lot about that in the last lesson. You might remember that when you have, say, stochastic gradient descent, where you're doing gradient descent for each example, you might have less accuracy. Your model might just, fit to certain examples instead of, okay, what do we need overall across all our examples? So it might be that you have, high bias because you're using that algorithm. Maybe you want to try out gradient descent with momentum, if you remember what that is. If those are just big words, that don't make sense, last video, go back review. Finally, the last thing that you could do is basically manual this thing. It just means go and look at, what is your algorithm getting wrong, one piece at a time manually. This is actually used to inform which features and parameters you add. So let's say, we look at the example above, all of the cat images. Maybe like you have no idea, why is, the test cost so high? And then you go back and look at the examples, it's getting wrong. And it's like, wow, these people are dressing up their cats. That's what the algorithm is not being able, that's what it's not able to figure out. So that can inform you, which kind of features, which kind of parameters might I need. Maybe I want to double down on the fact that cats usually have, eyes that have a certain position in the feature, in the image. So instead of relying on, say, oh, is there fur or not? Because, in this case, there isn't fur, but it's still a cat. We can rely on the eyes, maybe. And you might go about and, think, okay, how can we add features that say, are there eyes in this image or not? And maybe that's like a Boolean value that you could use while predicting, is there a cat or is there not? So that's one example of how you might, manually analyze each error so that you can figure out which are the right features or parameters to add. I hope these things make a little bit of sense. So that's how we can, act on high bias, how we can fix that problem. Now, what about if we have high variance? Now this time we have a completely separate, completely separate set of solutions that we can use. I'll explain all of them. So the first easy solution is just add more training data. The reason it is here, as I'll show you up above. Let's say, you actually had not just 1, 2, 3, 4, 5, 6, 7 training data points. That's a little bit, little. Let's say, you also had these intermediate ones and, some here, some here. Let's say you got out and, you collected more data points so that you could add them to this graph. So immediately you can see now the algorithm, it's not just, fitting to every single point on the line. And because of that, it won't be the case that C-train, it's so much smaller than C-test. And, that seems like a, non-advantage on both cases. One, we have a variance issue, and two, we just, got a higher cost. But remember, when you're doing gradient descent and you have more examples, well, maybe that leads the algorithm to have a little bit better of a line of fit, even if it, seems to overfit a little bit. So maybe, these curves, maybe they are oscillating a little bit less. That's what the algorithm learns. So you have less of a variance issue in any case when you have more training data. Now, with that in mind, it's often a joke in AI. Oh, algorithm's not doing well. Just go get more training data. There are unfortunately too many stories of like people. The first thing that they decide to do is let me go out and collect more data. And this is really expensive in the real world, okay? Like if if you're making a cat classifier, it's hard, You have to set up a photo shoot with cats. It's hard to collect more data. Or at the very least, you have to set up people who go out and look over the internet, try and download the right images. You have to pay those people. Especially this compounds if you have computer vision problems. Let's say, you're looking at self-driving cars. It's hard to get in, data on, oh yeah, here are all the sensors on my car and here are what they were doing and here are the images of the other cars around me. It's hard to get transcribed audio data. You have to pay people to do these things. So do not just, go get more data just because you feel like it. Okay, this should be like a later priority. This should be after you figured out that you have a high variance issue because your train cost is so much smaller than your test cost. Okay? That's why this is so important that we learn when do we have high variance and when do we have high bias. We don't want to spend months and thousands of dollars collecting data if we don't need to, if we actually have a bias issue. Another thing is, again, we can do manual error analysis to figure out, where are we going wrong. So when we change from the train examples to the test examples, is it really the case that we, did something that is ludicrous, that we actually treated this seriously? And it turns out, we had two different sources of data where, the test data had user images like this, and that's why the algorithm was having so much variance. The cost was increasing so much suddenly because we just didn't ever train the algorithm because we were looking at high quality stock photos. But more seriously, you can also have issues like, oh yeah, there's some variance here because we forgot that let's say you're trying to analyze writing instead. We forgot that people might write in this dialect, we forgot that people might have accented letters because they were writing in another language. So again, manual error analysis, it's one of the only techniques that's where you like specifically pinpoint, okay, let me go through the examples that my algorithm got wrong and manually think about, what is going wrong here? What am I missing? What kind of data would I need to provide the algorithm so it can learn to deal with this class of issues? Now, one last thing before we come to regularization. I'll explain what this word means, this fancy word, after this. One last thing here is now in the opposite case, before we were adding features, parameters, and layers, this time we got to remove features, parameters, and layers. So for example, we have like this sine of x to the 0 raised to the power of 5. We have that as a feature. It seems like it's a little bit too complicated. Okay, maybe I just want to, replace that with x0 raised to the power of 5. Like, never mind the sign business. So before we were adding this complexity when we had high bias. Now we're taking away this complexity. So completely opposite approaches. Now, let me actually explain what regularization is, this weird word. Let's say we don't remove, the features and their corresponding parameters, theta 0 times x0 to the 5. One thing that we can do is we can keep these other features and parameters, but we employ an approach called regularization, which basically just tries to keep the parameters small. So it's like, hey, you can have an x to the 5 parameter, but you can only have like 0.01 x to the 5. Yeah, you can't have like, a million x to the 5. You can't have 2,500 x to the 5. By the way, the 0.01, the million, etc., that corresponds to the parameters. So that's what regularization means. Keep the parameters small. Why does this help? It's because when we keep the coefficients, these parameters small, it's almost like they become more line-like. It's a simple way of saying it. If you don't believe me, try graphing. You can go to desmos.com, desmos.com. Try graphing, y is equal to x squared versus y is equal to 0.001 x squared. When the parameter, in front, the coefficients becomes really small, you'll see that this version, it basically looks like a line, very, 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 very gently sloped line. So when we keep our parameters small, it's kind of like we take, the curviness, the variance out, and we get a little bit more, flattish line. I hope that example is making sense. If not, again, desmos.com, try graphing those two examples. So that's the idea. When we have high bias, we want to not regularize as much. We want to maybe have, have larger parameters, larger coefficients, so that we have, less of a flattish line. Whereas later, with high variance, we want to add more regularization. We want to, take out the curves and we want to flatten this line. So we want to make our parameters smaller to do that. Keep in mind, this is not, this is not just for regression. This is for every AI algorithm that you can work on. And yeah, this isn't like a complete, set of tips on how can you fix these things, but it's a pretty good start. Just keep in mind that I'm giving, the regression example as an easy to understand example, just because it's easy to visualize. But in general, you can regularize, and then the intuition, you're flattening the line. It doesn't make as much sense, but that's the basic idea. So how do you actually regularize? That's the key question. The way that you do this is by adjusting the cost function. Why is that? Because let's say you want to keep parameters small. The way you can do that is by setting a penalty. So gradient descent is going to change the parameter values. You're going to set a penalty in the cost function that says, hey, make sure that you don't make these parameters too big, or else I'm going to punish you. So I'm going to show you how that works with our good old friend, the mean squared error function. Remember this simple cost function? So if we just had the unregularized version, where there is no regularization, then we could just have this formula where, it's looking at the difference between the predictions and the actual labels. And that's the way that we figure out what the cost is, how off our predictions. With regularization, what we do is we add a term to this. So this is still like all within, it's still all within the sigma operator. Sorry, this is within this sigma operator, and this is within this sigma operator. Sigma again just means the summation. So what's happening here? What's this weird stuff? Basically, we're going, remember, n is the number of parameters, also the number of input features. We're going through all of the theta parameters from theta 0 to theta n minus 1, and we square their values and add them all up. Why are we doing that? It's kind of literally like, oh, how big is the parameter, and we add that to the cost. So if you have a, larger, if you want to keep your parameters small with regularization, and then you have this term over here where, we're just squaring all the parameters and adding them to the cost, then the larger parameters are, the larger the cost is going to get. So it's kind of like a direct incentive in the cost function to keep your parameters small, otherwise the cost will increase. What's this stuff over here? So on the bottom, we're just dividing, just like we divide here, we're just dividing at the bottom by n. So we summed over n examples, then we divide by n. It's kind of like what is the average parameter size. So what is the average size of the parameter squared? And then we have lambda. This is the Greek letter lambda. It's a hyperparameter actually. What lambda basically does is it sets, a trade-off between this part of the cost, where the cost is based on, how different are the predictions from the examples, from the labels. And then this part of the cost, which is based on how big are the parameters. So let's say like lambda was equal to 0, then that just basically means like no net regularization, because if we multiply by 0, all of that stuff cancels out, right? So all of our cost is basically determined by how different are the predictions from the examples, from the labels. However, let's say, we set lambda, it's equal to 1,000,000. Then it doesn't even matter, what's going on here. Basically, the entire cost is coming from this term right here, because we're multiplying, whatever the parameter values are by 1,000,000. So the algorithm's basically going to go, oh boy, yeah, this is such a huge number. The only way I can reduce that is basically I set all the parameters to 0. So I use gradient descent to decrease all the parameters values, make them as small as possible. So what I'm saying is by adjusting lambda, you can adjust the strength of the regularization. From one extreme, it might be 0, which just means no regularization. We don't care about the size of the parameters values, because whatever they are, this stuff is going to get canceled out. And the other extreme is you set it to a really high number, like 1,000,000, and this part then doesn't even matter at all. Then we just focus on how do we reduce the parameter sizes, because that's what the cost is going to be mainly based on. Over here, I've just written that out. Basically, the way that we want to adjust, we have regularization hyperparameters in both cases. The way that we want to adjust them when we have a high bias versus a high variance. If we have a high bias issue, then the implication is that the lambda parameter is too high. Why is that? Because we are ignoring too much of this difference between the prediction and the value, because we set the lambda parameter too high. So if we're focusing too much on reducing the size of the parameters, we're not focusing enough on minimizing the difference between the predictions and the target outputs. So if lambda is too high, then we're going to get high bias. If lambda is too low, then we're going to get high variance. Not going to get, but that contributes to higher variance. Why is that? Because let's say we set it to 0 hypothetically, that's how low it got, then this stuff does not even matter. And all we're doing is minimizing the difference between the predictions and the labels. And if we chose a bad function, so that's what I meant, it's not always going to have high variance, but it's going to contribute to higher variance. If we chose like an overly complicated function, then there's nothing stopping the function gradient descent from adjusting the parameters so that it goes through every single data point. It's not going to be like, okay, we want to keep our curves relatively flat, so we're going to minimize our parameters to do that so that we can get relatively flat curves. It's just going to say, hey, you know what? You set regularization parameter too low, you set lambda too low, so you get high variance. So in each of these cases, to fix each of these problems, you want to do the opposite. So too high lambda, too high of the regularization parameter, you're going to get high bias. So if you are getting high bias, reduce the parameter size. Over here, if the parameter is too low, then you're going to get higher variance. So if you find that you are getting higher variance, then you can reduce the parameter size. Now this is again just one hyperparameter. You can adjust all sorts of other hyperparameters, and we're going to take a look at right after this, how do we adjust the different parameters, the different hyperparameters, besides just lambda here. Take a quick second to breathe if you're a little bit lost. Take a second to review this, because this is really important information. This is straight industry knowledge right here. You're going to be doing this all the time, so you got to understand this. One last technical aside right before we move on to how do we adjust all the other hyperparameters, not just lambda. This equation that I've shown you, the technical name for this is L2 regularization. Level 2 regularization. It stems from the fact that we have a 2 here. The 2 is being squared. As you can imagine, L1 regularization just means take out this 2. You just have every parameter to the exponent 1. There's also another type of, well, there's many other types of regularizations that you'll come across, so I'm just explaining the simple ones for now. Just keep in mind, there are others that are out there that you can look into. Especially you might want to search a type of regularization called dropouts after we've done the neural networks lesson. We often have dropout regularization used for neural networks. So search that up after the neural networks lesson. Hopefully you had a quick chance to take a breath in that moment. So now we're just going to wrap up. So we've talked about how do we fix bias and variance. We've talked about train test and validation data. Mainly we focused on these two. But now we're going to figure out how do we change our hyperparameters properly, and that's going to rely on the validation data set. Now, why use the validation data set? Well, because we spent all this time, with our test data sets, exploring these different relationships, trying to figure out what bias versus variance is. So it's, again, the same type of thing. The algorithm has seen the test data set by now. That's why we don't want to reuse it for the adjustment of the parameters, the hyperparameters, sorry. In reality, it's a little bit more reverse, where at the end, we're gonna, after we're done adjusting everything, we're gonna use the test data set to figure out at the end, we've selected our parameters, we've trained our model fully, including the hyperparameters. So then we're gonna, use the test data. We don't want to previously have also used the test data to adjust our hyperparameters. So that's why it's kind of in reverse, where we want to keep the validation data separate. We don't want to, at the end, ever have the model see the test data beforehand, whether we've been adjusting the parameters or the hyperparameters. So now let's get into it. So how do we actually adjust our hyperparameters? Basically, a bunch of visuals. I'm not even kidding. I mentioned, a few lessons ago when we were looking at pandas, visuals are so important when understanding data, but they're also really important when we're improving the performance of our AI models or AI algorithms. So I'm just going to show you a few useful visuals, just like above. I'm not going to show you every single approach, but I'm going to show you a few useful approaches. First visual I'm going to show you has to do with that regression algorithm earlier. Do you choose this fancy function over here, or do you choose, a simpler function? So earlier I just said, yeah, you can, compare the train and test data to see if you have a bias or variance problem. You can also visualize this so that you actually look at a bunch of different possibilities at the same time. So now we're actually going to use, C validation because we're adjusting what is basically a hyperparameter. Hyperparameter D is the degree of the polynomial that we're using while doing our regression. So like, is it degree 1? As you can see here, that's basically a linear function. Is it degree 2? This one is a quadratic function. Is it degree 3, cubic function, and so on. So on the bottom, we're adjusting our degrees. At the top, we're measuring, what is the cost for the train and for the validation. So remember, whenever you're doing the train cost and you have like these different degrees, well, the algorithm, it can just have high variance and it can overfit to the data. So you can have, a really complicated function like you saw above, where you can have, it goes through all the points, but it's just overly complicated. It's overfitting. So that will give you a low training cost, yeah. However, when you switch to, again, this completely different data set, now you're not training, now you're, running predictions. Well, you can see if you have, a really complicated polynomial, you have a high D value, like a 7, 8, 9, whatever, then you might have, the validation data, you might get a really high cost compared to your training data. Why? Remember what we said above. You can slightly modify each of these examples just because, you're getting new data sources. And now suddenly your, line of best fits that you overfitted, it doesn't fit so well. So classic variance problem. So when you get this relationship, early on, you're going to have high bias. That is this region over here, where both the new data set and the one that you've been training on, both of those give you, high costs. And then over here in this region, you have high variance, where the new data set suddenly has a lot higher of a cost than the training data sets that you've already seen, when you're training the model. So ideally, what you want is probably a point over here where you've minimized the new data set's cost as much as possible. In this case, the validation data set, not the test data sets. And then over here, at this point, you have kind of like the just right middle zone between having high bias and having high variance. Hopefully that's making sense. Here's another similar example. They're all going to be pretty similar, you'll see. This time let's look at cost versus the parameter lambda. So lambda again is the regularization parameter. As you increase the value of lambda, so let's say like this is 1,000,000 and over here is just 0. If the parameter is just 0, then in your training data you can overfit all you want. That doesn't exist, it's 0. Conversely, if you have lambda equal to 1,000,000, really high value, then this doesn't matter. It's just like, okay, make sure your parameters are small. That's why you can see when we run predictions on our training set, at the beginning, it can overfit all at once, but then later on, as we increase the lambda value, then the training cost is going to get a lot higher. Why? Because now we're not associating the performance of the algorithm with y hat, how much is the difference between the prediction and the label. In the case of the validation, early on, when we have no lambda at all, there's going to be a high variance problem where, initially the algorithm fit to the training data set, but it overfitted. So when it goes to then, try and make predictions on a new data set, the validation data set, then it's going to be really high. That's a bias problem because, sorry, that's a variance problem because you have a low training cost, and then with the new data set, you have a high cost. So this is the variance region of the algorithm, the values of lambda that will give you high variance. Over here, you have high bias because, at this point, because you adjusted lambda so high that it's only focused on minimizing the parameter values anymore, you don't have much focus on minimizing the difference between the predictions and the labels. So whether you're looking at this new data set or this data set that you already ran gradient descent on, doesn't matter, you're still going to get high values for both. So over here, this is the range of lambda that will give you, a bias problem. So over here, that is probably, close to the lambda you want, somewhere in the middle. That's like the just right region. Again, you'd actually make an algorithm where, you choose different lambda values. So maybe you go in increments of 10, 0.1, 1, 10, 100, so on, so that you can test out, different values and figure out, what is the just right lambda in my case. In this case, it's simpler, you're just choosing different degrees of polynomials. Hopefully you're starting to see a trend. We're just graphing the cost over the hyperparameter all the time. Let's do it again. So here's another way that we can diagnose, whether our algorithm could benefit from the more training data, trope, the thing that we always say, the joke. Yeah, just get more training data, I'll fix your algorithm. Will it actually? Well, you got to figure out, is it a high bias problem or a high variance problem? Here's another way to do this before, you go out and collect, millions of data points. Let's say you just, reserved 2,000 data points or, maybe less than 5,000. That would be a pretty reasonable small amount. You go from having like maybe one example to 5,000 examples in increments of whatever you choose, maybe like 100. And each time you're going to plot your training cost and your validation cost. So if you have a high bias problem, what's going to happen is your training cost at the beginning, it's going to be fine. Because let's say you have, just one scatter point and then you have to put a line through that. Well, that's pretty easy. There you go. There's my line. It always goes through it. Same thing with, you have just 2 examples. Yeah, I can always put a line through that. But then as you start getting lots of examples, then your training cost is going to start to increase. So it's going to plateau. So you can see now it's not fitting all the data properly. And especially what could make it plateau is like if your data is in a shape like this and you're just always graphing that. So no matter, how much more data that you add that's, in this other shape, you can see here the training cost is kind of plateauing. It's kind of flattening out. It's because you're not getting that much more wrong the more data you add, because, you're still the same-ish amount wrong, whether you had, this many training examples or a lot more. With the validation data set, so again, this one we haven't seen. So if, we just had one example and we just fit a line through that, we're like, whatever, could be that in the validation data set, we get an example like that. And now, oh, our cost is going to be really high. Same thing if we had just 2 examples, but then in the validation data set, like maybe we got a different 2. And now it's expecting a line like that. So you can see how with small examples, the validation cost will be really high. But then later on, it's always going to plateau again. Because even though the validation data might be different, let's say I do it in this other color, the high bias issue is still the same. We're maybe trying to graph a line where we really need a curve. So this is a key characteristic of the high bias issue. It's when you sample, what if I train with just one example, 100 examples, 200, 300, 400, and so on, you're going to find that there's this plateau where both the validation and the training costs flatten out. With variance, however, you're always going to have, the you're always going to have the validation cost decreasing. It's not going to flatten like you see here. You're always going to have the training cost increasing. It's not going to flatten. Why? Because, if you have more data, then remember you can have less variance, as we explained earlier, because your model has less opportunity to overfit. So that's why this is decreasing. However, as you add more data, because, it's harder to overfit, then that's why, during the actual training, we're not able to get as great results. So that's why this is increasing. So that's one difference that you can look out for when you're plotting these visuals. Again, that's the key point. We're plotting these visuals so we can figure out, do we adjust the number of examples, the lambda value, the degree of the polynomial, do we adjust it up or down? So if you find that, there's no flattening and there's always a gap between the new data source and the training data source, remember that's a key trait of a variance issue that we talked about up here. The new data set has a lot greater of a cost than the old data set, whether you're using the test or the validation data sets. That's going to be a high variance issue. So if you see this, then and only then is it valuable to go collect more data or go do any of these other approaches. Hopefully you're starting to see how, with just a simple graph, you can try and figure out what are the patterns here, what are the relationships, what do I need to do to make my algorithm better. With that being said though, we still haven't talked about the most important hyperparameter, which is alpha, the training cost, the one that we started with, the granddaddy of the hyperparameters. So let's wrap up with that. I want to remind you of something. The hyperparameter alpha, that's our learning rate. It controls how quickly do we go from, a point that is not the optimal theta value, it gives us a high cost, to the point that gives us the low cost. So if your theta value is right, then you only have to take a few steps to get there. If your theta value is way too slow, then you can see now you have to take a lot more steps than you need to get there. If your theta value is too high, sorry, I said theta, I meant alpha, learning rate alpha. If your alpha value is too high, what happens is you overshoot. You overshoot where you go past the lowest point and then you overshoot again and again, and you can see like the cost actually is increasing this time. So here you have a slow decrease in cost. Over here you have an increase in cost, and over here you have a just right cost decreasing over time. And that's what I literally am going to show you. When you have the cost, the training cost, this is during gradient descent. You want to map out this this function, this plot, sorry. With all of these others, you would kind of, do gradient descent first, and then, start messing about with the hyperparameters to see, given a certain set of fixed parameters, what change does the hyperparameter make? Over here, you want to do this during gradient descent. So if you get a graph like this, it steeply descends, and then it's starting to flatten out, then that means your alpha value, your hyperparameter, that is the learning rate, that is just fine. If it's just like a really slow descent, you can't even see the flattening out section, then that means your alpha value is too low. You should make the learning rate higher. And finally, if you see like weird bumps like this, then that means, your alpha value is too high. What's happening is your theta, values, they're overshooting. It's leading to the cost increasing over time. One last, technical note. When you actually plot these graphs, they won't look nice and smooth like this. They might look a little bit jagged. So you may have like it looks a lot more jagged. And especially, if you're doing stochastic gradient descent, then expect it to be like a lot more like this, randomly, with each, by the way, at the bottom, this t is the iteration, over time, the number of iterations that you do of gradient descent. There are methods that you can use to, deal with that issue so that you can get a clearer view, but we're not going to go into that today. So with that being said, that is the end of the lesson. I know that was a lot, but the key concepts are: why do we have training, test, and validation data? What is this bias versus variance thing? Based on whether we have bias or variance, how do we actually fix those things? Which steps do we take? And some diagnostic visuals that we can use to figure out, is it a bias problem? Or is it a variance problem? Or what? Like, what should we do? How should we adjust our hyperparameters? I hope this makes sense. I know it's a lot, so feel free to review, feel free to go over this again. But with that being said, we're almost done. The theory, the last thing we need to know is how, what is that weird neural network thing that everyone keeps talking about, and what are these layer things? So we'll be doing that soon.